Okay. Okay, so this lecture is going to be mostly on memory devices. So there is a lot of technical terms which are involved. I think it's okay if you are not working in this area not to remember all those terms. So just try to get the basic principle of how the memory devices work and what are the different types of memory devices that are available, because at the end of the day we are trying to mimic this synaptic functionality of the brain. Okay. Uh, Now, as we kind of mentioned, there are broadly two categories of memory. One is the volatile memory and the other is the non-volatile memory. Okay, the volatile memory is where you use a lot of this SRAM, the static random access memory, or the dynamic random access memory. Okay, these are generally extremely fast. SRAM is very fast and DRAM is actually very small. So you can actually store a lot of information in DRAM cells. And these are volatile. So once you switch off the power, everything is lost, right? While the non-volatile memory is something where you retain the information even when the power is off. And there are a wide variety of non-volatile memories. It starts from flash. Flash is the most common one that we all use. Our flash drive is literally flash. Most of these cloud or the data centers are really based on flash memory. Okay. And then we have the PC RAM, which is the phase change memory. Then MRAM, it could be magnetic random access memory. FET is ferroelectric field effect transistor. It's one of the emerging memory devices. Okay, this is still not out there commercially. So the first three are available commercially. Okay, but the last three are really not available commercially. They are like kind of still worked on. There are certain advantages. I will show that. And you have the RRAM, the resistive random access memory. And then there are lots of these emerging, like a nanomechanical one, polymer based one, molecular memory. There is a wide variety of these memory devices. Now, how do we benchmark? How do we know one memory is better than the other? So there has to be certain criteria on which we will judge, right? So one of the criteria is that how fast you can read the information from the memory and write information into the memory, right? So read and write speed. The second one is endurance, which means that how many times I can write and erase, write and erase, right? This is almost like your flash drive. Every time you kind of delete an image, that's like your erase operation, right? So how many times I can read and write is your endurance. Then the other is the retention, right? How long I can retain the information, whether it's for a day, for a month, for 10 years, or for eternity, right? That's another criteria of a memory device. And of course, the power consumption. At the end of the day, I need to make sure that my memory device is not consuming a lot of power. The other thing, when it comes to transistors, we also care about this memory window, memory ratio, memory density. Not as much important currently for this course. Then, of course, how small this memory device is, which is we call the footprint. Okay, or because smaller it is, you can scale it more. Because at the end of the day, I need more memory, right? So that's important. And how reliable it is. Right? If today you store one image, it got converted into another image tomorrow. You don't want such a memory device, right? So you need to really make sure it is reliable. It has to be thermally stable, right? Today it is like winter, and then I open my information in summer. You see everything is kind of flipped. That's not good, right? So thermal stability has to be there. It also has to be radiation resilient. That's like mostly for space application. But in general, because the memory devices are so small, all the time cosmic rays are coming and they can actually flit a bit, okay? And then my memory information gets changed. So there also has to be ideally radiation resilient. And of course, it has to be compatible with the technology, integration, and low cost, right? Today, your flash memory devices can store up to 1 terabyte of memory, right? Just 20 years back, when I was a graduate student, we used to use this, this floppy disk. 120 KB. Just think about in just last 20 years from KB to TB, right? That's like 10 to the power 9 improvement in the density. And today, those flash drives cost much less than what those floppy disks used to cost. Cost is a very important thing. That drives technology, no science, because the companies have to make profit, right? So just because you have a wonderful device, a twistonic device, Intel is not going to build it, right? It has to make them profit. Profit drives technology, not science. To some extent, science also tries, but it is very important. Cost is very important. Okay. Some loose connection is there. Huh? Hopefully it is stable. Okay. So now here I am comparing, these are the traditional technology which are out there. And you can see that no memory technology gives you everything, right? For example, SRAM, you can see that it could be, the cell factor means that how big it is. So SRAM is pretty big because it requires 6 transistors for each memory cell, right? So 50 to 200. So that number should be small. While you can see the DRAM and NAND flash are actually very small, right? While if you go to this row, right? While if you go to the write and erase speed, over here you see SRAM is the fastest, nanosecond, right? While look at your flash and your DRAM, right? Very slow, right? It's like microsecond or millisecond, correct? So although you want the speed to be the highest, the memory cell should be the smallest, not any technology gives you all the things, and that is why we have multiple different technologies available today for different applications, right? And flash is important because flash gives you very good density. And I don't know whether you have noticed, if you want to transfer some information from your laptop to your flash drive, you will see it always takes a longer time. It is much slower, while the other way around, if you are transferring information from your flash drive to your computer, much faster. Okay, because computer first shows it into SRAM and then it puts it into your non-volatile storage space. So this is where you see and then of course the power dissipation for flash is very low, while SRAM might be very high. Okay? And you can also do a similar comparison with the emerging technologies. That was mostly the existing one, and here is the one which compares all the emerging ones. And some of these emerging ones like FERAM, you can see it has most being in the green or yellow. Red is bad, green is very good, and yellow is somewhere in between. So you can then do a fair comparison between your flash, which is what we are using today, right, to store all this information in our cloud server, and you can see if I go to FERAM, I can really improve the the write power. You see the write power is high for the flash, but it is pretty low for the FEFET. So you can see there is a benefit of looking into these new memory technologies to reduce the power consumption of our AI eventually. Right? So this is a very good benchmarking table. For the sake of our discussion, we'll only focus on two things: flash, which is a more conventional type, and FEFET, which is a more emerging type. Okay, and we are trying to see how 2D materials can be used for both types of memories. Okay. So a flash memory device, I mean that now again is a little bit deep dive. I don't expect all of you to kind of understand the deep physics behind it, but in a flash memory what happens is, we talk about a transistor, right? A transistor has a gate oxide. Now the gate oxide for a flash memory device is designed in a very interesting manner. So you have actually a stack of 3 materials. So remember, in our last lecture, we had this figure, remember? So we have this channel, and then there is this oxide, correct? And then you have this gate, right? And this was your source, and this was your drain, right? And we spoke about how the oxide has to be very thin, it has to be very close to the channel. This was like our silicon. Remember this picture, right, from yesterday's lecture? Now this oxide for a flash memory device is actually designed in a way that there is not only one oxide, but this is kind of divided into 3 oxides. Okay, so this is like oxide 1, oxide 2, and then again oxide 1. Okay, 3 oxides are stacked on top of each other. Okay, why do we do that? So what we do is we make sure that the band gap of these 2 oxides are larger, and this has a smaller band gap. So now if I wanted to draw the band diagram, I am expecting all of you are aware of the basic band diagrams, right? If I want to draw the band diagram in this direction, how will it look? It has a large band gap material, right? This is like the conduction and the valence band, and the gap is very large. Then I have a small band gap material, and then I have a large band gap material. right? This is how the band structure will look like, right? This will be the conduction band, and this will be the valence band. This is for the large band gap material. This is for the small band gap, because this is the band gap, right? Remember, this is the band gap. This is clear for everyone? Okay. Now, this structure is very interesting. You see now, if some of you have taken some very fundamental course in physics, this guy over here, isn't that looks like a potential well? Right? Some kind of a potential well, where if I can put some charge over there, it will be very difficult for charge to come out, classically, right? Quantum mechanically, they can tunnel out, right? But if the barrier is very large, then they will not tunnel out. Right? So you see, I can use this for storage. If I can put charge over there, it will stay there forever, right? So I can trap charges, right? That is how your flash memory device works. Now the question is, how do I put charge in there, right? I have to enable injection, correct? Where can I get the carriers from? Because there is a channel, and this channel is, in general, if I apply a bias, have a lot of electrons or holes flowing through it based on whether it is N or P. So somehow, if I can get some of these charges and put it over there, I will be able to trap those charges, right? So how do I do that? Because without applying a gate bias, right, this channel is off, right? There is no carrier that is flowing. So I cannot really trap charges because there is no charge flowing in this channel anyways. But if I apply a gate bias, right, then there are charges, and when you apply a gate bias, the bands no longer remain flat, right, because they are going to get curved. So what will happen is, this will look like, let me exaggerate it a little bit, like this. Okay, there will be some more voltage drop over here, and there will be another one. Okay. Now what could happen is, you see, I mean, this is not drawn to the scale because this will be over here, because the band gap does not change, right? The band gap does not change, so the height will remain the same. Now you see that although, and there is a channel over here, remember, which has a lot of electrons, which is this way, right? Because we have now inverted it. So the channel is here. There is a lot of electrons available, but they cannot go in because there is a barrier. But now when I apply a bias, you see the barrier has become thinner over here. Make sense? Through which now they can quantum mechanically tunnel. Make sense? And once they are here, right, they are kind of trapped. Now if you remove the bias, right, then the charge cannot go back and it kind of stays there. This is what happens more, that's like a very easy way of drawing the band diagram. This is what is happening, as I told you, right? There is a smaller band gap material sandwiched between two large band gap material. One you make a little bit thicker, and one you make it a little bit thinner, because this is where you want to allow tunneling, and here you don't want to allow them to leave out to the gate, because you see, if it was also thin on the other side, it could have gone to the gate, right? You don't want them. That's why you keep this guy thick, this guy thin. You trap them between by applying bias. You see that the holes come in or the electrons come in based on whether it's an N-type or a P-type transistor. Make sense? Right? And then if you apply a reverse polarity, then you can again release them. Okay? So this is how a flash memory device works. Yes? You can in principle choose anything. This is what we have used, 3 nanometer of hafnium oxide. You can use any small band gap material sandwiched between two large band gap material. At the end of the day, you also want to make the transistors, well behaved. So you want a high K material in general. So it all depends upon how long you want to store, because even if the charges are here, you see, they can actually go out because of the quantum mechanical tunneling effect, right? So based on the thickness of this oxide, the dielectric constant, it will determine whether the charges will stay here for 10 years, 10 days, or forever. So it all depends upon the requirement, whether you are looking. Yes, yes, there is a mathematical relationship. So you can use the WKB approximation, maybe not known for everyone, but maybe for you guys, So this is a tunneling current. and the tunneling current is through a triangular barrier. And there's an expression for this tunneling current. You multiply the tunneling current with the amount of time you are applying the voltage. So current times time is charge, right? So that is the amount of charge you store into there, and that changes the threshold voltage of the device, right? So here are some cross-sectional TEM. This is something that we actually make in our lab, and you can kind of see the scale bar is 50 nanometer. So you can see the hafnia layer, the alumina layer, and the alumina layer over here, right? You can see from this contrast. There is also like elemental mapping. This is done using a cross-sectional TEM, transmission electron microscope. You can really map out all the elements where they are. I mean, that's kind of with a resolution which is like atomic scale. Okay? And this is what happens then. You can see that now what is happening is, once I program the device, these are like many devices, 50 memory devices measure. I get one kind of curve, and if I program it, it goes to another state. You see, so if I now were to measure the conductance at this point, you see here the device is off, here the device is on. So what I could do by applying a gate voltage, I could also do by storing information. When I store one state, the device is on. When I do not store that state, the device is off. Okay? And this is what we call the memory ratio, the ratio between the current when I store the information 1 and when I store the information 0. Right? Because when I read, I need to know from the current. If the current is high, then the information stored is 1. If the current read is very low, then the information is 0. Right? So that is the read and write operation. One is the write operation that I showed you, and then you read. For reading, you have to apply a small voltage across the gate, and you have to, and the source and drain, and have to measure the current. So that is how I define this quantity memory ratio, which is pretty high, 10 to the power 8. It's a very decent number. Then I spoke about the memory retention. How long can you retain it? And you can see that they are kind of flat. Once I put them in a particular state, they like stay there for a long time, right? So it becomes a non-volatile or a long-term memory. And I could actually switch between the two states multiple times, which is writing, erase, writing, erase, writing, erase, which is your endurance. Right? Right. Source drain material we are using is actually Ti gold, sometimes nickel gold, based on what makes a good contact to the 2D material. Channel. Yeah. Oh, you forget about this part. You forget about this part. This is just the substrate. You could use anything. You could use anything. Yeah, it's just a more complex substrate, but we don't really need to care about this part. I mean, the device principle happens over here. This we use it for different purposes actually. You can use glass. You can use any substrate. You can use simply silicon, right? So it doesn't have to be anything like this, because you're putting a metal on top. Once you put a metal on top, it doesn't matter whatever is underneath. Right. Yeah. Yes. This was for a different, it was for a different application. We are not going to talk about that, right? So you should be good with only the top part of the stack, and that is the functioning of the top part of the stack. Okay. Any question on this flash memory device? How it works, the principle? Good. Okay. And then you can see that it's very interesting. I showed you two states, right? 1 and 0. But that's really not the case. I can actually make the device at different states, because if I store different amount of charge, now instead of doing 0 and 1, I could do 0, 0, 0, 1, 1, 0, 1, 1. That is like storing 2 bit of information, right? For each state 0, 0, I get one conductance. Maybe this is 0, 0, 0, 1, 1, 0, 1, 1. So you can now start storing more information in a single device, right? So ideally, when a digital logic, we talk about a transistor, you can only store 1 or 0. But if it's an analog memory, you can actually store more information per device, which means now your footprint becomes smaller, your power dissipation becomes lower. Right? So we go from digital to more analog nature of this flash device memory. In fact, all the flash drives that we use today, they can store up to 3 bit of information. That means 8 different states: 000, 001, 010, 011, so all the different states can be stored in a single device, right. So that's the advantage, and you can kind of see that, I can change it with the pulse number, how many times I'm applying the voltage, or how long I apply the voltage. As I told you, most charge gets stored, so the conductance keeps changing. And this is very important because, in our brain, the synapse that we talked about, right, the connection between the two neurons, they keep getting updated as you, let's say, for example, read a book. So every time I read a book, the connection strength improves. Okay? Very similar, like the conductance of the device is improving, is very analogous to the strength of the two synapse connection is increasing. Right? Because at the end of the day, the synapses are conducting current between them, and they are actually updating the weight every time you learn something. And when the weight becomes very large, that means you have learned it very well, and it will take a long time to forget it, or it will be remembered forever. Right? So that's the idea of, kind of showing this aspect where you have a time dependent and pulse dependent. Pulse is like, how many times you read changes the conductance. Time is how long you read, it also changes the conductance. So this memory device can be mimicking the brain pretty well. Right? That's the take home message. And you can also erase it in the same manner. Right? If you want to forget this much, this is something the brain cannot do. And I will show you one of the advantage of this device is I can do gradual forgetting, or I could do an abrupt forgetting. This power, brain only has a power of forgetting, gradually. Right? That's why we see that, give yourself some time, things will heal. Right? If we were to forget immediately, any breakup happens, I will immediately forget. Then I am another, peaceful person again. Right? That doesn't happen. Right? So brain has some limitation which can now be overcome by using these devices. I could do both gradual forgetting or immediate forgetting. Right? This is the pulse. This is the number of pulse. This is the number of pulses that we are applying. And the other one is the HCS is the high conductance state, and LCS is the low conductance state. So one where the conductance is high, and the other where the conductance is low. Okay? And you can say I can also do the same thing. The forgetting part or the erasing part, I could do it both the pulse number as well as with the amount of time or duration of time I apply that pulse. Yeah, for each of these it is done at 100 milliseconds, and here you can see also faster, right, down to almost 100 microseconds. So you can actually have a wide range of speed for these devices based on how fast you want to learn or how fast you want to forget. Which GD is the conductance. GD is the conductance. GD is the value of the conductance. That's why we say high conductance state and low conductance state. So it goes from a high conductance state to a low conductance state, or vice versa. Good. Okay. And you can see, each state kind of is stable, but with some decay. You see, although I'm putting it to so if I wanted to kind of completely learn, it kind of starts to forget a little bit. This is literally what the brain does. You can put it into a state, it starts forgetting no matter what, right? The same thing. If you want to forget something, it starts to relearn back again. Okay. So that aspect is kind of captured in this device. Okay. And this is some of the long-term memory retention. I think this is not as relevant given the diverse background of this group. But we do a lot of other studies on these memory devices just to benchmark it with other memory technologies. Okay, and then you can actually use an N-type transistor, a P-type transistor. You can do it with the CMOS capability, because at the end of the day, I was talking about is in-memory compute, because the silicon technology is CMOS, right? And your memory technology is completely different, right? Based on this NAND flash or NOR flash devices, we are trying to merge them together for in-memory compute. So that's why we are showing that it can be applied to both NMOS and PMOS. NMOS is made out of MOS2. The PMOS is made out of tungsten selenide. We did not cover the N-type and P-type FETs in the two other lectures. But at the end of the day, some of you may have seen how a N-type transistor looks like, how a P-type transistor looks like, and I can program and reprogram both the N and P-type transistor. That's the take-home message from this slide. Okay, so that we can integrate memory with logic, for a CMOS logic. Okay, now let's move on to, yes. CMOS means N and P. So that's why I have to integrate the memory with both N and P, and that is what we were showing. Only N. Only N. That's why I'm showing this one slide where we are showing that eventually I have to make an analog CMOS memory. Right? The previous one was NMOS. Not ambipolar. Ambipolar devices can never be used. Okay, ambipolar devices are generally useless. You have to make an NFET and a PFET. NFET should not have a P branch. A PFET should not have an N branch. Yes.
You have used MOS, right? Now it's depending on the thickness, it changes from N type to P type, right?
No. MOS2 remains mostly N type. Making a P type MOS2 is very difficult. Tungsten selenide you can get N and P, but MOS2 you cannot. There is no much thickness dependence of MOS2. These are all monolayers. These are all monolayers because I told you at the very first yesterday's lecture that unless you use a monolayer, you cannot scale them. Because we have to have back off in our mind that we need to at the end of the day make the devices very small. And the reason to go to this 2D material is to make them thin. Now, if I start making a transistor with a very thick MOS, I lose the purpose. Why not then use silicon? Because silicon can already be 6 nanometer thick, and that's our FinFET technology. So we have to use thin layers of MOS2 and WSE2, right? That's the very basic, because that is where the advantage of 2D material lies. Now I'm saying that, okay, with that, can I integrate memory, which I cannot do with silicon technology right now. So that's why this is very important, where we are able to show analog CMOS memory. Make sense? It could be in seconds, it could be in hours, it could be in years. The model. So this is essentially the memory ratio, or we are talking about that one. So this is a number. This is a number, right? So memory ratio is just a number. Okay, this part. Any other question? Yes. Which one? But this is read only. You cannot write, because I mean, at the end of the day, when we talk about any artificial intelligence and neuromorphic computing, you should be able to write it again and again. That is what we call the weight update, right? Whether it is for the I mean, training, even in some instances, I mean, inference may not require, right? I mean, you should be able to only read, do not need to write. But generally, ROM is not too heavily used nowadays. I mean, you have to use a memory where you can both read and write. That is something that we need for neuromorphic applications. Right? Any other question on the flash? Okay, so now we'll go into another type of memory, okay, which is the ferroelectric memory. Yes. Yeah, sure. You can do that. You can do that. In fact, a lot of publications are there where people are actually using MOS2 and using it as a 2-terminal memory device. Now, these memory strip devices have their own advantages, right? Because this 2-terminal, they could be even smaller because there is no need for 3rd terminal. But also has certain disadvantages because they can only store information and cannot do computation. Transistors are good for both computation as well as storage. So when you are thinking about really a multifunctional device, 3-terminal device gives you a lot more flexibility compared to a 2-terminal device. But having said that, you can use MOS2 as a memory strip memory. Right. So I think maybe I will talk to you about the previous lecture, because I think the idea of, so we are talking about 2 different devices. For transistor, I need a thin channel, and that is where I want to use my monolayer MOS2. You are talking about a memory strip device. There I don't think there is a requirement that it has to be a monolayer. You can actually do multiple layers because it's a 2-terminal vertical device. Right? There is no scaling law, there is no Moore's law for memristors, right? And it does a different function altogether. So therefore, I think the requirement is very application specific, right? Okay. Any other question? Okay, then let's move into ferroelectric field effect transistor. That's a very big space. Okay, we are going to cover only a little bit of that. I mean, people spend their entire career on ferroelectric field effect transistor, which we are going to cover only in maybe 20 minutes. So we work on that as well. So the ferroelectric materials are very unique. Okay, let's say for example, the most common ferroelectric material is barium titanate. And you can see how the barium, titanium, and oxygen atoms are kind of arranged, right? So the titanium atom is at the middle, right? But this titanium atom is actually not exactly at the middle. It is shifted either a little bit upward or a little bit downward. Okay, and because of that, the charge center for the barium and oxygen is at the center of that, this cube. But because the barium the titanium atom is not sitting at the center, so the charge neutrality point is no longer there, and you create a dipole moment because you have a positive and a negative charge, and that is the direction of the dipole moment, which gives you a polarization. Okay, so ferroelectric materials are unique because naturally they are either in the up direction, up polarization, or down polarization. It's almost like this material has this 1 and 0 stage. Right, without doing all those charge injection or anything, I already start with a material that has information storage capability. Right, I simply need to switch the polarization. That will be my writing, right, and somehow I need to read it. Right, so this is very unique about this, this peroxides materials. We did not shift. This is how the material is. When you make this material, whether you get it naturally or if you actually grow this material, this is how the material kind of comes out. This is a peroxide material. Okay? And there is a huge class of material. There is lead, zirconium, titanate. There is correct. Not H3. I mean, it could be those as well, right? But I think you can generally oxygen is there in most of this material. PZT is another one. STO if you dope it. And this is the polarization versus electric field, which means that your polarization will not switch until and unless you apply a critical electric field. If you just apply a small electric field, the polarization will stay in one direction. Once you cross that critical field, it will switch, right? So that gives you a window, almost like our memory window, right? So that I have a window of operation. So now if I, instead of replacing this oxide, right, if I replace it by a ferroelectric material, right, that's where I was storing information. I simply replace it by a ferroelectric. Up polarization will give a certain conductance state. Down polarization will give a certain conductance state. And that is how a ferroelectric field effect transistor will work. Okay. What's the advantage? Switching this polarization is extremely energy efficient. Okay. You can actually switch this polarization with almost like picojoules of energy. So that's the advantage. Why are we interested in this kind of memory device? And what happens is literally, what I was showing in the two states. When I switch the two different direction of polarization, you can kind of see that the band diagram of the channel changes. So once it becomes like more N, it becomes more P, and these are the reading. Because in order to read, you need to change the conductance of the channel by changing the polarization direction, right? And that's what happens in a ferroelectric field effect transistor. Okay, good. Any question on this? This is very fundamental, right? I mean, you have to, because that's the right, right? So one is the right. When you're writing, you're changing the direction of polarization. Channel doesn't always has to be on because your writing is happening in this direction, right? While your reading is in this direction. They're kind of separate, right? So you can make the channel on, right? You can switch the polarization, you can make the channel off and also switch the polarization. So the gate voltage versus the conductance of the channel is still like a transistor, because at the end of the day, it is a transistor, but now there will be a hysteresis window. This is how the characteristics will now look like, because earlier I was to have unique characteristics, right? Now this happens when I sweep the gate voltage, because once the polarization switches, when it comes back, it is in a different state. And then if I go to much more negative, the polarization again switches, then I come back to another state. So now you see I get two different conducting states, right? You can use 2D material. We are going to use 2D material, but I am saying is that you can actually even use it with silicon. But the problem is, as I told you, just perovskites. Just because I have a perovskite material and silicon, I cannot actually integrate them, right? Because you have to grow these two oxide. Oxides can be easily grown. We have silicon oxide, which is a native oxide, grows very nicely. How am I going to grow barium titanate on silicon? Because these material requires epitaxy. Okay? So integrating these has been challenging. Otherwise, FEFETs will be today a commercial technology, right? But now we can do it with 2D materials. You see, 2D because I can transfer. And I don't really care about growing the barium titanate or strontium titanate on top of it. That's what I'm going to show you actually. That's what we did. Okay? But there is also a very long history of this ferroelectric field effect transistors from Rochley Sol. It goes back to 100 years when the ferroelectric material was first discovered, right? Barium titanate, PZT were discovered in like almost 60, 70 years back, right? But the first FEFET was kind of conceptualized 1974. But still today we don't have an FEFET commercially available. And it has been really an engineering challenge, a materials challenge, that how do you grow this perovskites on top of these things. So, and then this could be used for neuronal circuits and stuff, which we'll probably come to. And then more recently, people have discovered that if you take hafnium oxide, which we were talking about for the high K, right, which we could integrate with silicon, people were able to show that hafnium oxide, when doped, may actually become ferroelectric. Right? So now that integration challenge is mitigated. You see, because I can do an ALD process to grow hafnium oxide, dope it, it becomes ferroelectric. So that is a big field right now. It is like generally, zirconium doped, silicon doped, or aluminum doped hafnium oxide becomes ferroelectric. Okay? So that's kind of very interesting. And then there are also 2D ferroelectric material. We talked about this entire this gamut of 2D material. There are some like copper, indium phosphide, sulfide. It's actually a ferroelectric material. So now you can use a ferroelectric oxide on top of a ferroelectric 2D channel, right? And then you can make an FEFET as well. And then there are some other works. Right, so this is 80 based FEFET. You can kind of see the atomistic imaging. You can literally see the silicon atoms. Right? This is like cross-sectional TEM. These oxides are mostly amorphous, so you will not see really nice crystal structure over there. But as I told you, right, I mean, there's also even with 80, you actually have to heat it at a very high temperature to make it ferroelectric after it is deposited, and that is mostly not allowed once the silicon transistors are made. There is a back end of the line limitation. And this is exactly why some of the 2D materials are going to be very important. I mean, there's a lot of information over here. Huh? What is interlayer? There is an interlayer. There's a lot of details of that. Okay, I will not go into this, but if you're interested, I can talk to you afterwards. We have a lot of time for discussion, right? Even in the evening and stuff, we can discuss about. If you're interested in this topic, I have way more slides that we could put in over there, because ferroelectric, I told you, is a topic that is there for 100 years, and it's not possible for me to cover it in 20 minutes. I'm just trying to give you the gist of what has happened, and what are we trying to do. So we are actually trying to create this nano membranes of strontium titanate. So as I told you, earlier days this could only be grown on an epitaxial substrate. This LAO is actually lanthanum based substrate, but now there are some interesting techniques that has been discovered, where you can put a sacrificial layer of strontium oxide, which is also epitaxially matched, and grow this strontium oxide films, and this strontium oxide layer can be dissolved in water. Okay, which means now I can create a 3D film. Like we've talked about 2D films, nanosheets, we can create nanosheets of strontium titanate. And once you can delaminate it, you can put it on anything, right? So and these grow very high quality. Because one of the main advantage of this perovskite is that their epitaxial nature, their crystallinity, and you can preserve the crystallinity and yet get this nanofilms. We actually collaborate. We don't do it. This is our collaborators from University of Minnesota who make this material, and then we get these materials, and then we start integrating them. Right. So now you see an MOS2 channel which is sitting on top of this strontium titanate. Okay, so we make this device. There's a cross sectional TEM. Here you can see the STO over here, and MOS2 you can't see even because it's just monolayer, but if you zoom in, you can kind of see the MOS2, right? And you can see the molybdenum and sulfide atoms. This is STO, all the strontium titanate, and all the stack that we generally use. Okay, so we can now start combining a 2D and 3D material to make these FETs. And then we go ahead and measure some devices. This is not as relevant, but now if I do the characterization, you see, this is what we expected, right? This hysteresis window. So now if I measure at 0, there are 2 conductance states, right? That is one for the up polarization, another is for the down polarization. So that's what a 2D FET would look like, and now I can also use this as a memory device. Okay, these are some second harmonic generation measurement just to confirm that there are polarization orders. Again, exotic measurement techniques. We have all these capabilities in Penn State, so we kind of do everything. And there are certain ideas about this particular ferroelectric, but then you have to look into retention. As I told you, a memory device has to be retentive. Otherwise, what is memory if I cannot retain it, right? But now you see there's some problem. You see that the high conductance state is going down. That means after some time, the memory states will march. That means I have forgotten everything, okay? Which is somehow good for some brain application, brain memetic application, right? But then we have started looking into these devices. We do some more characterization, and we started looking into these devices at different temperatures, okay? And we found that at lower temperature, the memory becomes absolutely stable, okay? So this device, as of it today, cannot be used at room temperature. So maybe not for neuromorphic computing, but this could be very important for cryogenic memory devices for quantum computing. Okay, because quantum computing also requires you to have peripheral electronics which can operate at a very low temperature. And today we don't have a memory technology that can operate at low temperature because charges freeze out. Okay, flash memory devices are not good for low temperature. So for quantum application, this kind of memory device could be a key. Okay, not for memory, but I just wanted to give you an idea. We can actually get more room temperature ferroelectric 2D FETs. Currently, we are working on that. We are working on films like BST, barium strontium titanate, which has room temperature ferroelectricity. But the idea is very much the same, right? And then we show that these transistors were big. We did not scaled everything. These were the very first demonstration. These transistors were 1 micrometer long, 1 micrometer to 500 nanometer channel length. Okay, and then you can see one very good thing about this is we get 10 years of projected retention, right, for these devices. The switching is very fast, as I told you, right? That is the advantage. Flash memory devices are very slow, hundreds of microseconds. Here it is like nanoseconds, right? Switching voltage is very low. Okay, endurance is pretty good, and in a single device, I can store 64 memory states. That is what? That is 2 to the power 6, right? 6 bit in a single device. The flash today can do 3 bit, right? So huge amount of memory storage capability a single device can give, right? So that's also the advantage of now integrating these exotic materials on top of each other, which we could not do with the traditional technology, right? So that is why 2D is also interesting, right? This aspect of it. It's a multi-bit memory cell, and it happens just because when you switch the polarization, there are multiple domains, and not all domains switch at the same time. If you have switched some of the domains, that will lead to a certain threshold voltage, and that will give you these different memory states. As you go to more and more memory states, you can now see that this starts to fall on top of each other, right? Then it is not distinguishable. That is bad, right? Because then I do not know whether I stored 0001 or 0010, right? So you also have to have this memory ratio. That's why we are talking about both the memory ratio is also important. So as you keep increasing number of states, nothing is free, right? Then you lose your noise margin. Now you cannot reliably operate this memory, right? Because one memory states overlap with the other, right? But eventually, we can get up to like 6 bit. Beyond 6 bits, it will become extremely, variable, right? And you can operate this at 15 Kelvin, right? And if it operates at 15 Kelvin, because this polarization switching, you can actually even operate even lower temperature, right? Because the switching of polarization is going to happen at all temperatures. even at a very low temperature. Only if you go to very high temperature, the ferroelectric property is lost. This temperature called Curie temperature, right? And the Curie temperature for these devices are actually pretty high, hundreds of degrees centigrade. Okay? No, we measure multiple times. We program it, then we measure it. We program it again and again measure it. Program it and again measure it. Yes, yes. Because in order to go to a different state, you need to write it first. So first is the write, and then you read. Right? So you write for one test, you read it, and then you keep doing that. Right? So this is all about the ferroelectric memory. Let's take some questions on this part. This is also quite a lot. I know that with the FEFET and the flash memory devices, but this will form the basis of the neuromorphic devices that we're going to discuss later. So although if you don't need to understand the entirety, but at least understand the very core or the basic of how different memory devices work. Because when we go to the brain mimetic circuits, we'll be using these memory devices alongside light, tactile sensation, chemical information. We'll merge everything together. So just make sure that you understand the basic of the memory devices. Okay? Any questions? Okay, you have too many. I don't. Okay, so what's your question? So when you are growing this material, you are talking about the growth, or after making the device, operating the device. You are going to dope that material. So why do you want to dope that material? It's not ferromagnetic. Ferromagnetic is a very different class of material. Ferroelectricity is a very different class of material, right? So we are not talking about ferromagnetism here at all. White. This is ferroelectric. This is ferroelectric. Okay. So we are not doping it to make it ferromagnetic. There are ferromagnetic materials. We are not going to talk about that in this course. Okay. There are also even 2D ferromagnets. We're not going to talk about ferromagnets are generally more metallic. They are not semiconducting or insulating. These oxides are insulating because remember we're using it in a transistor. So at the end of the day, this has to be an insulator. That's a very basic requirement. So these ferroelectric materials are also insulators. Most of the ferromagnetic materials are not. Okay. So no matter what. So I mean, so now you have a question or temperature dependency on what? During the growth? I mean, you grow these materials at relatively high temperatures. Does that answer? I don't know. I mean, I'm trying to understand your question. So you grow these materials at a very high temperature. Based on the temperature of the growth, the epitaxy, the defects, and everything may change, right? So that is the synthesis problem, right? You of course you want to optimize to get the highest quality of the crystal that you are growing, right? So temperature will play an important role over there. Temperature plays an important role no matter what you grow, whether it's 2D material, non-2D material. Temperature has a huge role to play because that is how the reaction kinetics is all governed by temperature. Any other questions? Yeah, we'll look into that. Yes. No, I just showed you, right? Multiple states. Multiple conductance states means simply that you can store more information. Yeah. Multi-bit, yeah. Yeah, I mean, I have also given all the papers. Okay, so if you are interested in any particular topic, you can simply read that paper. Okay, these are all published paper. Nature Communication is an open access journal, so these are all open access. So if you want to download and read about that paper, you can do that. Correct, correct, correct. In this state, there is no high conductance and low conductance. The high conductance and low conductance only comes when I am storing 0 and 1, 0 and 1, 2 bit. Otherwise, it's analog. So you cannot really call high and low. High and low only is like digital, right, or binary. Once you go to a digital memory, you can say high and low. If it's analog memory, you simply say that how many bits you can store in that device. Okay, good. Then should we take again another 5 minutes break and then come back and talk about, now light will come in. So from electron we'll go to photons.